9th lecture in the course Signals and Systems, and this lecture is titled Fourier and his series. Before we take up introducing Fourier, there is a small amount of discussion left from systems described by difference equations, described by constant coefficient linear difference equations, which we would like to discuss first before introducing Fourier. We said that the general form would be ak y of n minus k summation k equals minus infinity to plus infinity in general equals to bk x of n minus k equals to, a very mistake, finite difference equations. We cannot have infinite difference equations, so this should be capital N and the lower limit should be 0, the present output. Alright, and here also k equal to 0 to some capital N. This is the general difference equation describing a discrete time system, and in the context of this we have already introduced the terms FIR and IIR, finite impulse response and infinite impulse response, and also the two terms recursive and non-recursive. We have said that recursive, in general, IIR systems are described by recursive equations and FIR systems are described by non-recursive equations in general and usually, but one is not identical to the other. In other words, an IIR system can be computed non-recursively and FIR system can be computed recursively, and we took one example to illustrate this particular fact. As we did in the case of the continuous time systems, let's take an example, and the example we take is a simple first order difference equation yn minus half y of n minus 1 equals to xn. In order to solve this equation, this is the first order, and therefore we require one initial condition. We cannot accommodate more than one. Just one initial condition, and let this initial condition be y of minus 1. Let's say this be some constant a. Alright, initial condition, and let us say that we wish to compute y of n, that is the output, when x of n is equal to some k multiplied by delta n. That is, all we are doing is to find the impulse response, but not of strength unity. It is of strength k. To do that, we can do it recursively. That is, we can write y of n as equal to x of n plus half y of n minus 1. Alright, and if I take n equal to 0, we can take n equal to 0, y of 0 would be x of n exists only at n equal to 0. This is k delta n, and therefore it shows its state only when n equal to 0. It does not have any other effect. So at n equal to 0 the value is k plus half y of minus 1 is a, that is given, so half a. Alright, next we find out y of 1. In computing y of 1, when n is equal to 1, k delta n term drops out because delta n exists only at n equal to 0, and therefore y of 1 is half of y of 0, that is equal to half k plus half a. And if we continue this, I might record this later. If we continue this, y of 2 would be half y of 1. So this would be half to the power 2 k plus half a. And in general, if we continue this recursion, we get y of n as equal to half to the power n k plus half a, alright, which I can write of course as half to the power n plus 1 a plus k times half to the power n. And the condition is, what did we compute here? We computed for n equal to 0, 1, 2 and so on. In other words, for n greater than or equal to 0. Now let's compute for n less than 0. If n is less than 0, you recall our original equation is yn minus half y of n minus 1 equals to xn. We want to go backwards, that is, we used to compute y of minus 1, y of minus 2, y of minus 3 and so on. Now for that, obviously we have to change the form of the equation. We express y of n minus 1. These things will become matters of routine when you go deep into discrete time systems. To introduce this, there is no trick in this, straightforward. What we want to do is, we want to compute y of n minus 1 from y of n. And therefore we write the equation slightly differently. We write as twice y of n minus twice x of n. Is that okay? We multiply by 2 and we take this to the left hand side, bring this to the right hand side. So this is what I get. And for n less than 0, this term twice xn only shows its teeth at n equal to 0. So n less than 0, this term is equal to 0. Alright. Therefore, my equation is simply y of n minus 1 equal to twice yn. And we have already the initial condition y of minus 1 equal to a. That means we know the value for n equal to 0, and therefore y of minus 2, which would be twice y of minus 1, is simply 2a. Y of minus 3 similarly would be 2 squared times a. Alright. And if I continue this, then I get y of minus n as equal to 2 to the power n minus 1 a. Agreed? What is the value of n? I have already taken y of minus n, therefore n is greater than 0. That is correct. I have already taken minus n. Now if I write in terms of, if I write for n less than 0, then I should write y of n as equal to 2 to the power minus n minus 1 times a, which I can write as half to the power n plus 1 a. Agreed? This is the equation for n less than 0. If I compare this with the equation for n greater than 0, you recall the solution. Well, let me write this again. Y n greater than equal to 0, y of n was half to the power n plus 1 a plus k times, what was the value? Half to the power n. And therefore if I compare, there is a k, yes, I have written a k. If I compare this equation is valid for n less than 0 and this equation is valid for n greater than equal to 0, I can write the general solution as, y of n half to the power n plus 1a. This term is common to this as well as this, and this term comes only when n is greater than or equal to 0. So what I do is I multiply this by u of n. This is valid for all n. This is the general solution. And you notice that if the input is 0, what was the input? Input was k delta n, a unit impulse. If the input is 0, then k is 0. And if k is 0, the output is not 0 because the initial condition, because of the initial condition a, that is y of minus 1. And the only way that we can make the output 0 would be to make the initial condition equal to 0, which is exactly similar to the continuous time case. That is, the system, this simple first order difference equation system, y of n minus half y of n minus 1 equal to x of n, would be linear if the initial condition is 0, that is a equal to 0. Only then x of n equals to 0 shall lead to y of n equal to 0, and the system shall be linear. In an exactly similar manner, we can also investigate the causality, and we can show that the difference equation system or the discrete time system described by this difference equation will be causal if and only if x of n equal to 0 for n less than equal to n0 implies causality if and only if x of n equal to 0, n less than equal to n0 implies y of n equal to 0, n less than equal to n0, which simply means that in language it simply means that before the input is applied, the output should not be there. Output should be identically equal to 0. Now you notice the difference is, as in the continuous time systems, this is a repetition, but I am doing it intentionally so that it gets imprinted in your mind. What it states is not a spot condition. You know, your initial condition equal to 0, this is a spot condition. In other words, it holds at one value of time or time index n. On the other hand, causality requires a range, a condition in a range, and this range is infinite. That is, n less than equal to n0 means n starts from minus infinity to n0. Alright, so it's a range of n or a range of time. It is not a spot condition, and if the output is being forced to remain 0 for n less than equal to n0, this satisfies the conditions of causality. And exactly as in the continuous time domain, if a linear system, if a linear discrete time system is causal, you can show that this is also time invariant. That is, initial system in the initial state implies linearity, causality, and also time invariance. In most of the practical cases, this is the type of system that we shall be concerned with. With this brief discussion on discrete time systems and their describing equation, we now go over to one of the most important tools of system analysis, linear time invariant systems. Linear time invariant systems, whether continuous time or discrete time doesn't matter. One of the most important tools of analysis and synthesis was introduced by this man Fourier. We would like to know who Fourier was and what is his contribution. We start with Fourier's series, which is the simplest. The full name of Fourier, like our Andhra names, has three initials: Jean Baptiste Joseph Fourier, J.B.J. Fourier, a Frenchman who looked like this. That's Fourier. There is a small correction here. He was born in 1768 and died in 1830. Very colorful career, and you can draw many parallels with the present conditions in the world and in India in particular. Fourier's main work was published in 1822, a greatly influential pioneer work on the mathematical theory of heat conduction was published by the great French mathematician, Egyptologist, that is a person who knows, who is very scholarly and knowledgeable about Egypt, exactly like Indologist. You know, there are professorships in the United States universities on Indology, that is one who is very conversant about India, its history, its culture and tradition. Similarly, Fourier was an Egyptologist and administrator, Jean-Baptiste Joseph Fourier. It was a masterpiece not only because of the new field of heat conduction that it explored, but also because of the infinite series of sinusoids, and that is the contribution, infinite series of sinusoids that it developed. The latter, this infinite series of sinusoids, became known as the Fourier series. About Fourier's contribution, Fourier's series, Lord Kelvin, who was known as William Thomson before he became the Lord, says Fourier series is a great mathematical poem, and indeed it is so. Who was this person Fourier? Fourier was born in France, a small village, Auxerre, the son of a tailor. He attended a local military school conducted by Benedictine monks and showed such proficiency in mathematics that he later became a mathematics teacher in the school. Like most Frenchmen his age, he was swept into politics of the French Revolution and its aftermath, and more than once, twice to be precise, he was about to be guillotined because of his involvement in politics. He was one of the, fortunately not, then Fourier series would not have been there, and 205N would have been taught in a different manner. He was one of the first teachers in the newly formed École Polytechnique and later became its professor of mathematical analysis. At age 30, he hobnobbed with the current administrator of France, who was no other than Napoleon Bonaparte, and he was appointed scientific advisor, exactly like scientific advisor to the Minister of Defense. We have a position in India. There are such positions all throughout the world. Napoleon appointed him as his scientific advisor on an expedition to Egypt. Napoleon went to Egypt and Fourier accompanied him, and for 4 years he was the secretary of the Institute of Egypt, the work of which marked Egyptology as a separate discipline. It was with Fourier that Egyptology started. He was prefect of the department at a university from 1801 to 1814, where he wrote his famous treatise on heat conduction. This treatise was examined by 4 great mathematicians of the age, one of whom was Laplace, and Laplace rejected the thesis. It was several years later that Laplace himself generalized Fourier's work. These are the interesting points of history. He completed a book on algebraic equation just before his death in 1830. This was Fourier, and it is his work that we are going to study in great details in the whole of this course on signals and systems. In fact, Fourier series, Fourier transforms, spectrum, amplitude, phase and everything, that all comes from Fourier. To introduce the Fourier series, nothing is known about Fourier's family life, so I didn't include this. Whenever I get an opportunity, I'll let you know. The Fourier series, the motivation is the following. You have seen that any general discrete time signal x of n can always be written as a summation of basic signals, and the basic signal is delta of n, that is the unit impulse, any general discrete time signal. In a similar manner, x of t can be written in terms of x of tau delta t minus tau d tau. That is, any general signal can be written in terms of a unit impulse function. It is as if in this summation the signal x of n is being decomposed into a large number of signals and being superimposed on each other, and then we take linearity and time invariance to be able to analyze a system. That is, what we do is, we have seen so far, what we do is we find out h of n, that is the response of the system to delta n, and then weight these responses by x of k and sum them up, so that y of n is simply summation x of k h of n minus k, the impulse response, which we have said is the convolution relationship. In a similar manner, what is summation in discrete time system is integration in continuous time system, and an arbitrary x of t is now being decomposed into an infinite number or a continuum of elementary signals, each of which is a delta function. And if we know the response to the delta function, then the output can be written as a superimposition of all the outputs, and therefore we get what is known as the continuous time convolution. The Fourier series, instead of delta t, there is nothing sacred about delta t. Delta t is as good an elementary signal as any other elementary signal. We could even use u of t, or even its integral, the unit ramp function r of t. We have seen that if we know the impulse response, then we know the unit step response. One is the integral of the other, or one is the differential of the other. In a similar manner, we know that if we know h of n, then we also know psi of n. Psi of n minus psi of n minus 1 is equal to h of n. We have proved that relationship. Alright, and therefore instead of working with delta functions, we could also work with unit step or unit ramp. A fourth candidate in this category is the sinusoidal function, sine omega t or cosine omega t. That is also an elementary signal, and its generalization is in terms of e to the power j omega t. Real part is the cosine omega 0 t, the imaginary part is the sine omega 0 t, and therefore we can work instead of delta t, u of t and r of t, we could work in terms of an exponential signal. Exponential signal takes into itself both categories, that is sine as well as cosine. These are real signals. If it's a complex signal, a combination of sine and cosine, well, this is good enough. A further generalization of the elementary signal is e to the power st, where s is in general a complex quantity, sigma plus j omega. Alright, it has a real part, it has an imaginary part. The beauty of these signals is, that is the exponential signal of the form e to the st, whether you take sigma equal to 0 or non-zero doesn't matter. The beauty is that if you have a linear time invariant system, then the response of the system to a signal like this is of exactly the same form. That is, the response is also e to the st, perhaps multiplied by a constant. That is, it's the amplitude which changes, but not the shape or the form. To show this, let's recall that if you have a linear system, we are talking now of a continuous time system. We introduced Fourier series in the context of a continuous time system. You know that for a linear time invariant system, if delta t leads to h of t, then an arbitrary signal x of t leads to an output which is equal to integral minus infinity to infinity x of t minus tau h tau d tau. Alright. Now, if x of t is the elementary exponential signal e to the st, then you see y of t becomes equal to minus infinity to infinity e to the power s t minus tau h tau d tau, of which small t is a constant as far as this integration is concerned, because the integrating variable is tau, it's not t. So the term containing t can be taken out. If I do that, let me write this again. Y of t equals to minus infinity to infinity e to the power s t minus tau h tau d tau. If I take e to the st out, then I get e to the st integral minus infinity to infinity h tau e to the minus s tau d tau. Now, as far as t is concerned, as far as the actual time is concerned, I am interested in finding the output at time t. And in the right hand side you see t occurs only in this term. This integral is a constant as far as small t is concerned, because tau is a dummy variable and this is a definite integral from minus infinity to plus infinity, and therefore this is a constant. Let's call this constant as h of s. It is only a function of s. Tau drops out because it's a definite integral. So my y of t becomes equal to e to the st h of s. And what is this response due to? My x of t was equal to e to the st. We therefore prove that if x of t is the elementary signal e to the st, then y of t is of the same form e to the st, except that there is a multiplicative constant which is h of s. Now e to the st is not a solitary function of this kind. There are many other functions which, when fed as excitation to a continuous time linear time invariant system, produces the same function multiplied by a constant. Such functions, of which e to the st is only an example, is called by the great name eigenfunction. E to the st is an eigenfunction, and the response of the system is now characterized. If you feed an eigenfunction to the system, then the response to the system is the same function except for multiplication by a constant, and this constant is known as eigenvalue for the system. You will come across these terms again when you study control systems, but I thought it is an appropriate point to introduce the terms eigenfunction and eigenvalue. If I ask you to define an eigenfunction is a function which, when excites a linear time invariant system, produces the same function multiplied by a constant, and this constant is known as the eigenvalue for the system. I repeat this because it's an important concept. Now I write this again. X of t is equal to e to the st produces y of t equal to h of s e to the st. Now if the system is linear, then you see, if I take an input like a1 e to the s1t plus a2 e to the s2t, two such eigenfunctions combined linearly with weights a1 and a2, then the output should be y of t. Now this constant shall vary. That is, instead of s, we shall have h of s1 a1 e to the s1t plus a2 h of s2 e to the s2t. And in general, if I put an x of t which is a summation of ai e to the sit, summation over I, if this is my input, then the output shall be equal to summation ai, again summation over I, h of si times e to the power sit. This follows from linearity of the system, and that's where the series, Fourier series, comes. That is, if you are given an input which can be decomposed like this, which can be written as summation ai e to the SIT. E to the SIT being an eigenfunction produces the same type of response, that is, it is also e to the SIT, except that linearity, not linearity, a subclass of a sub-property of linearity, namely homogeneity, says that it must be multiplied by ai, and in addition, because of e to the SIT being an eigenfunction, it also multiplies by another constant h of Si. Alright, this is the root of Fourier series. In fact, Fourier series, the seed of Fourier series was shown by the same gentleman who is associated with e to the j theta equal to cosine theta plus j sine theta. What's his name? Euler. What is his first name? Leonhard Euler. Euler was working on vibrating string. Most of the musical instruments consist of vibrating string. Some are, what do you call them? Percussion instrument. Some are on a string, wind instrument. Okay. But sarod and sitar, guitar, they are all plucked, bowed or struck string. And Euler was investigating a string tied to two posts and then plucked at some point. And you know what happens. Now you know. Euler didn't know. When Euler investigated, he didn't know. Well, he observed that there are sinusoidal variations and that these variations vary with time, and he in fact hypothesized that the vibration of a stretched string, whatever manner you excite it, one should be able to decompose this vibration into sinusoids, that is sines and cosines. This is where the original idea lay. But Euler did not pursue this to a great extent. Also, he faced stiff opposition from the then physicists and also mathematicians. They didn't wish to give sine waves or sine functions the importance that is due to them. This is where Fourier started from. Fourier started from this, and we are doing it exactly the way that Fourier got the idea. Fourier was not a very rigorous mathematician. Unfortunately, he was good in mathematics, but that rigor he lacked, and therefore he went more by physical